So welcome back, everyone. You can type your attendance as usual in the chat box. We will start the lecture straight away. And regarding a lecture video, I'm intending to upload the lecture video, but thing is that I don't have a broadband connection at home right now because there's some problem with my BSNL broadband connection. As and when my BSNL broadband is working, then that time I will upload all the videos. Uh, so in the meantime, I think we can just continue our usual lecture. I don't want to upload all this large video file using my mobile phone data. So you have to wait for that. So this is what we have discussed. These are the fundamentals of this semiconducting property and semiconductors. And one thing you should note here is that even when we do a n-type doping means pentavalent doping. You are inserting a pentavalent atom here. Pentavalent atom you are inserting in the silicon crystal. So you should know here that insertion of one pentavalent atom result in one uh, donor impurity contributes to one electron. Insertion of one pentavalent atom contributes to one free electron. So this free electron is loosely bound to this pentavalent atom and it can easily get detached and then become a free electron. So by inserting this pentavalent atom, we are inserting the whole atom as you see here. We are inserting the whole atom. So you know that when you are inserting a whole atom, an atom contains equal number of protons and electrons, right? The number of protons at the nucleus and the number of electrons revolving around the nucleus is always equal in an isolated atom. Uh, so, uh, so by inserting one pentavalent atom, even though we are contributing to one free electron, the number of protons and the number of electrons inserted in the silicon crystal, they are always equal. So your silicon crystal, even after doping with pentavalent atom, will remain electrically neutral. And similarly for this trivalent atom doping, that is inserting one trivalent atom here, you are inserting equal number of protons and new electrons in this boron atom. So in the silicon crystal, you are just replacing one of the silicon atom with boron atom. Even though you created a vacancy here in the valence band or in the covalent bonding, you created a vacancy, but the number of positive charge particles and a number of negative charge particles inserted in the silicon crystal in this p-type doping is also equal. So they remain electrically neutral. So, as we discussed, uh, one pentavalent atom like Pb and all, when we insert one electron, two electron, three electron, four electron, all these four electrons, they are forming covalent bonding. They are forming covalent bonding with neighboring silicons. They are forming covalent bonding here. But the fifth electron is, as I said just now also, it is loosely bound to this atom. Okay, this is loosely bound to the atom. So as it is loosely bound to the atom, by giving even a very small amount of thermal energy, that is at room temperature 3 upon 2 kT is a very thermal energy. So even at room temperature, the thermal energy will be sufficient to dislodge this electron and become a free electron. So when you look at this particular system in energy band diagram here, energy band concept here, energy band concept here. If you are looking at this energy band perspective, you will find that the energy state of this electron, The energy state of this electron, which is loosely bound to this lead atom, is actually somewhere here. The energy state is somewhere here, which we call it donor level. So you see that this is the valence band, the bottom side is the valence band, and the top side is the conduction band. Okay, this is the conduction band. So since you can easily make this electron as a free electron even at room temperature because of this thermal energy, you can see that the electron in this energy band perspective is the energy state of this electron is lying very, very close to the conduction band. So it can easily jump to the conduction band and become a free electron readily available for any electrical conduction. Okay, so because of that, we denote the donor level to be very, very close to this. The energy or the donor level or the energy state of this donor electron is lying very, very close to the conduction band. They can easily become a free electron by gaining even a very, very small amount of thermal energy and jumping to this conduction band. Okay, and similarly, uh, this p-type doping, this is the p-type doping. In p-type doping, the acceptor level, we call it, is very, very close to the valence band, because what do we call this acceptor level? See, by inserting this p-type atom, trivalent atom here, you are creating a vacancy here. The energy state of this particular energy level that is created here is very, very close to the valence band, because from the neighboring, let's say this is another silicon, from the neighboring atoms which are in the covalent bonding or which are in the valence band, if these atoms are participating in the covalent bonding, they are in the valence band. Okay, that's what we interpret like that in the energy band diagram. They are in the valence band. So these things can easily jump to this vacant state. These things can easily jump to this vacant state. So even at room temperature, you have sufficient energy to transfer this electron to this, to occupy this to this, and then jump back, and so on and so forth. So the energy state of the vacancy or the hole created when you insert a trivalent atom, which we call it acceptor level here. It is very, very close to the acceptor level, is very close to the valence band here. This is your valence band and this is your conduction band. Because of that energy state, which is very close to the valence band, you see that electrons in the valence band, which are in the covalent bonding, they can now easily jump to this acceptor level and easily return to this valence band. Okay, so that is how we define it as acceptor level and donor level. You should know that donor level is lying close to the conduction band, as for the reason I have just mentioned, and also acceptor level is close to the valence band. Now, see, we all know that in a conductor also, if you take a copper wire also, a copper wire as it is, it does not conduct electricity. So in order to have a copper wire to conduct electricity, you need to apply a certain voltage, right? So if you pass a but if you connect a copper wire good conductor to this battery, the potential source, then because of that action of the battery, the copper will start conducting electricity. So what is electricity? Electricity, as we know, it is simply a movement of charge carriers, like free electrons in the case of a conductor. But as I said, in semiconductors, in addition to free electrons, we can also have holes, right? We can also have holes. So, so the holes and the electrons, they will move under the action of external applied voltage or electric field. So, suppose I take a semiconductor block here, and this semiconductor, let's say it's having electrons and holes. Under without any external field, these electrons and holes, they will have a random thermal motion, as I said before. So they will move randomly in any direction, And because of that randomness in direction, you don't have any net transfer of charge and no electrical current without any external field. Okay, so now suppose I connect this to an external voltage source like this. This is positive terminal, this is negative terminal. So if you connect it like this, if V is the potential you apply here, and if L is the length here, if L is the length here, then the electric field within this, the electric field will be in this direction. The electric field within this will be V, the potential you apply divided by the length here. Okay. So this is the relation between the fundamental relation between potential and electric field. So the electric field within this semiconductor will be uh, potential applied V upon length. So under the action of this electric field, these charge carriers like electrons and holes, they will start moving, and electrons will move in this direction. So, sorry, electrons will move towards the positive terminal of the battery, and holes will move towards the negative terminal of the battery, like we discussed yesterday. So now instead of traveling in random direction, electrons and holes transfer will occur in a specific direction, and this will result in a net transfer of charge. And the net transfer of charge is resulting your net current, your net current. Okay. Now, now the question is, how quickly these charge carriers in a semiconductor like electrons and holes will move within the solid. How quickly the electrons and holes will move within the solid under the action of this external electric field, which you apply using your potential source here. So that is what we know as, or what we define as a drift velocity. Okay, drift velocity. So under the action of the external field, the electrons and holes, the charge carriers, they will move within the solid semiconductor, and that movement is called drifting under the external field. And the velocity attained in the process is called drift velocity. Okay, drift velocity. And if you apply more voltage, then you will have more electric field. If you have more electric field, the drift velocity of the charge carriers also increase. Therefore, we have the fundamental relation that the drift velocity is directly proportional to electric field. More electric field means the velocity gained by the kinetic energy gained by the electron, or the velocity gained by the electron will also be in, increase. Okay, will also be increased. So therefore we see that this is directly proportional, and the proportionality constant is called mobility of that particular charge carrier. Mobility is a measure of, sorry, mobility is an intrinsic property of the particular semiconductor. So mobility, it is a measure of how quickly the electron can move. It's a measure of how quickly the electrons can move under the action of external field. Okay, so this is an intrinsic property of a specific conductor. So depending on the type of semiconductor you choose, like silicons, germanium, and there are various other type of semiconductors like gallium arsenide, zinc sulfide, and all these things. So depending on the solids you choose, the charge carriers will have different mobility, the proportionality constant here, right? So similarly, we also know that like if you apply electric field here, vacancy or hole, they will also move, and the drift velocity of the hole is also proportional to the applied electric field, and the proportionality constant is again called mobility of that uh, hole, the charge carrier. Just a minute.
Let's pakataom. At hiyam siya. No nito. Ano fine kan hostel bula kanyan umakwarta lang dua.
Okay. So now we have introduced two terms. One is called drift velocity. So drift velocity is simply the velocity gained by the charge carrier, like electrons and holes, under the action of external electric field. And now also we introduce mobility, which is a proportionality constant here, which is an intrinsic property of the semiconductor you choose. So depending on the material, the semiconductor, the charge carriers will have different mobility. And also another point you should note here is that uh, mobility of mobility of holes is always less than mobility of electrons. The reason is that effective mass of hole effective mass of hole is much greater than effective mass of electron. So you will study about effective mass of electrons and effective mass of holes in your solid state course in 6th semester. Thing is that why do we say that hole mobility is always less than electron mobility? The reason is that if you look at this, if you look at this figure once again, the electron conduction here, it will occur only when the electron is released in the valence band. Okay, when the electron is released in the when the electron is released in the conduction band, they become free electron. They are not bound to any atom. They are not bound to any atom, so they can move freely as if they are a very light particle. They can move freely once once the electrons are in the conduction band. Under the action of external electric field, they will move freely. They will move freely because they are not bound to any particular atom or any chemical bonding. They are just freely available within the solid. They can just move freely. Just a minute. I'm having.
Saat ito ang lowa ko hold your breath.
Warm water. Ilong. Now, when we talk about electrical conduction due to holes, we also said that holes are in the valence band. The movement of holes occur within the valence band that we have already mentioned. And from here also you see that I have already talked about this. Holes is just a vacancy in the covalent bonding. So the transfer of holes from one covalent bonding to another covalent bonding will occur when you apply electric field, such that under the action of this applied electric field, electrons in the neighboring covalent bonding can jump to this vacancy. Once this electron jumps to this vacancy, it will occupy this vacancy location, and vice versa, you will find that this vacancy will be shifted to this location. So therefore, the vacancy is shifted to this, the vacancy is shifted to this, and the vacancy is shifted to this. So the movement of holes, as you see, it is within the valence band, or it is simply the shifting of vacancy from one covalent bonding to another covalent bonding. Now, as you see, this involves the electrons which are, this involves the shifting of electrons which are tightly bound to these atoms in the covalent bonding. So these electrons, which was earlier tightly bound to this covalent bonding here, under the action of external field, they shift to this vacancy, and the vacancy also shifted in the reverse direction. So effectively, in order to move the hole or vacancy from one place to another place within the solid, yeah, it involves shifting of electrons in the covalent bonding from one place to another place. Right? You agree with me here? So because of that, uh, uh, the mobility, or how quickly or how easily a hole can transfer, a hole can move, is quite low. So mobility is a measure of how effectively or how quickly the charge carrier can move, right? So since it involves the chemical bonding, chemical bonding, shifting of electrons from one chemical bonding to another chemical bonding here, so the transfer of charge is a very, very slow process. And therefore the effective mass, so in energy concept, it will appear as if hole will have a very large effective mass. A hole will appear like a very heavy particle, right? Holes will appear like a very heavy particle in energy concept, because it is very difficult to sieve a hole from one covalent bonding to another covalent bonding in comparison to the freely available electrons, which are not bound to any atom. They can easily move, right? So with here, because of this, we say that effective mass of holes is quite large. Holes are very heavy in comparison to free electrons. Okay, and therefore mobility, how easily the charge carriers can move, mobility of holes will be much less than the mobility of electrons. Okay, remember that. So what is the time now? All right, now let us come to what we define as, let us also introduce another term called current density. Current density, as the name suggests, current density simply means it is the current per unit volume. Density means it is per unit volume. Okay, current per unit volume. So current, as we know it, it is the rate of flow of charge. So charge per unit time and per volume. Volume means length into cross-sectional area. Length into cross-sectional area. Suppose I have a semiconductor like this. So this will be the length. And what is the cross-sectional area? Area will be, this is the width, this is the thickness. So the cross-sectional area A here will be equal to W into T. Width into thickness, W into T is the cross-sectional area. All right. So length into cross-sectional area will give me the volume, per unit volume. Now, N is actually total number of free electrons. N equals total total number of free electrons upon volume. Okay, charge density means total charge density of free electrons means total number of free electrons per unit volume. Volume is length into cross-sectional area. Now, what is VE? VE is simply the velocity of motion of charged particles like electron. VE velocity will be, uh, suppose electrons move from this to this within 1 second. So VE will be length upon time. VE will be length upon time dimensionally. Now, if you write this in terms of dimension, JE will be equal to current density will be equal to charge. This is the negative charge of an electron into d velocity will be length upon time dimensionally, and N is number of electrons, total number of electrons upon length into cross-sectional area volume. Total free electrons per unit volume, right? L and L will cancel out. Therefore, you will find that minus of E, that is the charge into number of charged particles upon time. This will give me current, right? This will give me the current. So, and per unit area, right? So this will give me the current. per unit area. Sorry, I should when we talk about this current density, we always talk about current per unit cross sectional area. Cross sectional area. Okay, A is a cross sectional area. So J, the current density, is number of charged particles transferred per unit cross sectional area. Per unit cross sectional area. Okay. Now, so you can prove that dimensionally also. J is simply current per unit cross sectional area. So this is how we define a current density, current per unit cross sectional area. N is total number of free electrons per unit volume. So now if you put all this dimensionally, you will find that this mass of E into VE into N will result in current per unit cross sectional area. And here simply we put a negative charge for an electron here. For an electron, we put a negative charge. VE is the mobility, sorry, the drift velocity of an electron. Drift velocity of an electron will be mobility into electric field. So sorry, I should put a arrow vector sign here. All these things. Current density is we consider it as a vector. Okay. So current per unit area. Now, yeah, now dimensionally correct. So here we define a new term called conductivity. Conductivity, sigma, is simply mass of E into mobility into charge carrier. So this is the conductivity of an electron, the conductivity of an electron. And similar to that, we can also calculate, we can also obtain the current density and the conductivity of hole. So for holes, the drift velocity is VH. So let me put in this vector sign here. So the drift velocity of holes is mobility into electric field applied. So if you again define the conductivity of holes as electronic charge of the hole multiplied by mobility of holes into P, which is the density of holes, number density of holes. This is the total number of holes per unit volume. Now, as I said before, in intrinsic semiconductors, electrons and holes are always formed in pair. So in order to have like silicon here, all this covalent bonding it forms with the neighboring silicon. So in order to have electrons, free electrons, one of these electrons will have to be dislodged by the thermal energy. By dislodging, you will create a hole also. So electrons and holes are always formed in pair in a intrinsic semiconductor. Therefore, the number density of electrons equals number density of holes. And this quantity, they are very small. Okay, they are very small. So in intrinsic semiconductors, the amount of free electrons and the amount of holes available due to the thermal energy is usually very small, and they are always equal. Okay, so the total current will have to be current contribution from electrons, current contribution from holes. So let us put a vector sign here all the place. So current density of electrons is sigma E into E. Current density of holes is this, and you will find that in intrinsic semiconductor, the conductivity is given by this. This is intrinsic semiconductor conductivity. For extrinsic semiconductors like N-type, so let's say in one particular silicon, let's say we have 10,000 silicon atoms, and 10,000 silicon atoms, and suppose you insert 4,000 lead atom or any other pentavalent atom, lead or arsenic or any other pentavalent atom. So that means in these 10,000 silicon atoms, you will be having 4,000 free electrons. because we said that one pentavalent atom contributes one free electron. So we will have these many free electrons. These many free electrons we will have. So if you compare the number of free electrons introduced by this doping with the number of free electrons introduced due to this electron hole pair formation here, the electron contribution from the doping is much greater than the electron contribution from this electron hole pair, because at room temperature, unless you heat up your semiconductor, the number of electron hole pair formation chances due to room thermal energy is very less. So only very less amount of electron and holes will be formed due to the thermal energy of dislodging of covalent bonding. Only very few quantities, let's say in about 100 only. 100 free electrons and 100 holes are formed by thermal energy 3 upon 2 kT, and you are inserting 4000 arsenic atom or lead atom, means the number density of this doping, the number density of doping, that is the number of dopant atom per unit volume, the number of dopant atom per unit volume is quite large. If that is quite large, then the contribution by the thermal energy, that is around 100 only, will be negligible. So we can say that in n-type semiconductors, the number of free electrons is approximately equal to the number density of the dopant atom. If that is the case, you see that now that we have large quantity of free electrons and very small quantity of holes, so electron is now majority, holes are now minority. So minority charge carriers, holes, electrons are majority charge carriers in n-type semiconductor. So when that happens, you will find that your current contribution by the electron will be much greater than the current contribution by the holes. Therefore, the contribution of current by the holes can be neglected in n-type semiconductor. So in n-type semiconductor, we can simply write the current density in n-type semiconductor is J equal to JE. We are neglecting your contribution of the holes because holes are in minority, only about 100 out of your 4000 donor atoms, like pentavalent atoms. You are having 4000 free electrons already from the donor atom, and you are only having 100 holes because of the thermal energy. So therefore the conductivity will be simply this. The conductivity contribution from your holes can be neglected. Okay, so I think I will stop here because of the hiccup and all. I couldn't complete what I intended to do. We will continue from here in the next class. So if you have typed your attendance, we can end the session. Okay, now I feel better, but our time is up. We have only 3 minutes or so. Yeah, you can leave the meeting. So I would like to continue from this point next semester, next class tomorrow. Okay.
Thank you, sir.
Sir.
Thank you, sir.
Thank you, sir.